What makes the billboard smart is that it always have the object turned towards you no matter where you are. So what it's used for is that objects that would be far away, such as a tree or a mountain, like a mountain in this case, would always be turned towards you, so that you don't have to render out a 3D mountain no matter how far away it is. As you can see on long distance, this works just fine. However, when you move up close, you can easily see that it's the same mountain all the way around, which would not be ideal. Therefore, when you get up close, you usually exchange these billboards with a 3D model instead, so that it's not the same on all sides. And now to explain the code for this. We start out by defining this as a shader called billboard, and then we have our properties. We make a scope for them, and inside here we have just one property for this code, which is a 2D texture with a default that's white, and it's called texture image. We then go to a subshader, create a subshader inside of our shader. A subshader is made to contain a list of passes. A subshader can also contain a tag that would be common to all the passes inside of this subshader. I will explain tags in a bit. And inside the subshader we have a pass. For this assignment we only need one pass, as we have a pretty simple piece of code that does not need to be separated up in different parts. For example, if we were doing an object with both reflection and refraction, we would need two different passes, one for each. Or if we were doing something where we have to analyze different light sources, we could then have one that calculated for instance the ambient light, and one pass that calculates how the texture or how the object would be affected by a spotlight. And passes can also have individual tags. These tags is used to define when the passes or the subshader should be rendered in the renderer queue, which I will explain a bit of. A renderer queue is smart to or the renderer queue is used to render different parts of the scene at different times so that they overlap each other correctly. In a standard renderer queue, you will first render the background, which will be, for instance, the skybox. Then you render out all the geometry. This is the default queue. So this is where our shader go, as it doesn't have any tags. Then it is rendered in the geometry part, and we want it to be rendered in the geometry part, as it changes the geometry of our model. So therefore this works just fine for us. We then have a alpha test, which is the geometry that, or alpha tested geometry is smart to render after the real geometry, as this is more efficient, or it's more efficient to render the alpha tested objects after all the solid ones are drawn. Then we render out the transparent objects, for instance glass and particles and all this, and then we render out an overlay which could be lens flares or graphical user interfaces. It is also possible to kinda create your own queue by saying that, for instance, you want something drawn right after geometry, but it doesn't really fit into the alpha test stage of the rendering queue. Then you could say that it should be rendered in the geometry +1. So it's rendered right after geometry instead of together with the rest of the geometry. And back to the code. We then head to this CG program, which starts a snippet. CG program is the start of a CG snippet, a computer graphics snippet, which means that this will contain some computer graphics code, and the CG program also comes with a lot of predefined functions and variables that are very useful when doing computer graphics. For instance, the vertex and the fragment shaders that we use here. You can tell this program to compile, well, that you need a vertex shader compiled by using this pragma. Then it says that you would compile this vertex shader and that the vertex shader is called vert. Same goes for the fragment or pixel shader, that you tell that to compile as the as the name frag. We then head to our uniforms. In this case we only have one uniform. Uniform is the initialization of our texture, of our properties. In this case our texture. Say to uniform it as a sample 2D, and then give it the name that we gave it up here in properties. We also have our then we head to our two structs. We have a struct for input and one for output. The input simply takes in vertex positions, the positions of the vertices in our model as a 4-point float, meaning that it has 4 float values. The reason it has 4 and not 3 is that we have our x, y, and z, and then we have a homogeneous coordinate which is just 1, so that we can multiply it with our 4.4 view matrices. And we then have our output down here, which also has a position. The reason this one is called SV position instead of just position is that it's basically the same, but you use SV position for outputs. The output also have a texture, texture coordinates. The reason why the input doesn't have this is because we calculate the texture coordinates according to the model's coordinates. As when we get the model in first, it doesn't have a texture yet. Only when this shader is run through, it will have a texture. So there are no texture coordinates to take in besides from the main texture. Then we head to our vertex shader down here, which takes in our struct input, and it outputs it is of this type vertex output, so that it will output this struct format, which we can then we initialize a struct called output of the type vertex output that we've defined up here. Now this line is where the magic happens, is where we calculate our new positions. We do this by first multiplying multiplying the view matrix model times view, and we multiply this by 0.0.0 because we wanted to have the same origin. We transform it according to the origin, so therefore it should be 0.0.0. This fourth value is a scale. Normally it would be 1. I've chosen to make it 0.2 here, so that it would, the object would be bigger, as when you make the viewpoint smaller, the object would be bigger as it fills up more of the viewport. And then you simply add the model's vertices to this, and then you transform it all into the projection plane, which is what you can see on the screen. And I would like to explain this with a drawing, as I find that easier. Here we have our world space. It is the big space, big coordinate system that contains everything in our scene, both the object, the camera, the light sources, everything. All this is 3D, but I've chosen it, or I've drawn it in 2D seen from above, as make it easier to see with my limited paint skills. Here we have an object with its own coordinate system, the object space. We use this to do object-centered transforms, such as rotating the object around its own axis and such. Then we have the cameras. The view space is what the camera can see, where we have this triangle out here, which is actually a pyramid. And it should end in the origin. It's a bit off here in this drawing. And that is the view space. That is what the camera can see. And what this transform we are doing is that we are transforming it according to the viewpoint's origin, which means that all the faces that can be seen from there will be rendered out, and we are transforming it according to the this origin of the viewpoint, so that it will always be facing that way. The normal of the visible plane will point towards this origin. And then it is transformed into the projection plane, which is basically what we can see on our screen. The projection plane ranges from -1 to 1 on both axes, so -1 is over here, +1 is over here, -1 up here, or -1 down here, and +1 up here. So that this point down here is 1.-1, and this point up here is -1.1. And then we head back to the code again to get through the last few parts. This one calculates the texture position on the object's plane, or the visible plane of this cube. The reason why it is offset, we simply set it to the vertex X and the vertex Y, and then with a small offset. The reason why we have this offset is that the standard cube in Unity has its origin in the middle, so it ranges from -0.5 to 0.5, whereas a standard texture ranges from 0 to 1. So we would have to add 0.1 to that, so that it ranges from 0 to 1 instead of -0.5 to 0.5. And then we return the output struct to this vertex fragment, to the fragment shader, our pixel shader. And what the pixel shader does is basically that it takes the point in the main text that fits with the point in our text input texture coordinate, and then paints them, and it does this for the whole face, so that our texture is applied to the visible surface. And then we end our CG program piece of snippet, so that or our snippet of that, as we don't, as this is the end of the program. And that is all I have for now. Hope it was satisfactory.